Okay, everybody, so the quiz is tomorrow. It's going to be 8 or 9 questions long. I forget if it was 8 or 9, but some of them are fairly involved, so I'm going to give you a little extra time. I'll give you about 20 minutes for that. It should be plenty of time, but some of them, if you don't know how to work them, it might take you a little longer to stumble through them. It's only from Chapter 8. So let's look at Chapter 8 questions. If y'all really want to move into Chapter 9 today, we can, but let's just look at Chapter 8, I think. All right. You will see torques, like a Newton's second law problem, where you have to find the net torque and then also apply Newton's second law. So you will see a problem like that. We'll look at those first. And then you'll see, moment of inertia, you'll see angular momentum, you'll see rotational kinetic energy, and translational kinetic energy. We've done all those types of problems in class. You'll see conceptual problems and calculation problems. I just want to remind you that the quiz questions, they come directly from the old exams. So just look at those old exams for practice. And even if you're just memorizing the answers, don't do that. I don't think that's very helpful. But even if it's just that you're really familiar with the questions and you know the answers just from looking at them, that's fine too. I still think that kind of practice is useful to help you become more familiar with it. Okay, so let's look mostly exam 4s. I think actually probably all exam 4s. So I can tell some of these, like on this exam 4, these things are all kinematics and angles and the like. If you have any questions about which questions on a particular exam are on the quiz, just let me know. Let's find, can we do one like number 16 and 17? It'll be something like that. If you look on the exams, they're all sort of similar. Let's see. Okay, so for number 16, the first thing you have to do here is find the net torque. And the first thing you do there is you say, okay, which of these forces provide a torque and which don't? In this case, I'm rotating about C, so I know that force provides no torque at all. And then I ask which ones are positive and which ones are negative. Clockwise is negative, counterclockwise is positive. This force right here causes it to rotate in this direction, so that is a negative torque. And this one causes it to rotate in that direction, so that is a positive torque, because this is clockwise and this is counterclockwise. Okay? I think we're good on that, right? We did that on the last exam. You had a question very similar to this on the last exam, but you'll see it again on the quiz tomorrow. So the net torque is going to, I'll call this torque 1, torque 2, is negative torque 1 plus torque 2. That's the force times the length of the moment arm, which is the distance from the point where the force is attached to the axis of rotation. So that's 25 times 2 meters plus the force, which is 10 newtons, 2 meters, sine of 30. And so that's equal to negative 50 minus 10, negative 40 Newton meters. And so it's 40 Newton meters clockwise. Hopefully that's easy for you. So we had that on the last test. But the next question is the one that's different. On this question, you have several steps. I'm going to do it over on the left for number 17, looking at 17. The first thing you need to do is find the moment of inertia. Okay? And so we look for the kind of shape that it is. This is a bar. And so you look on your table. I'm going to give you the equation sheet. I'm not giving you the full equation sheet, just the part for Chapter 8 and then the table with all the shapes on it. And so this is a bar, and the moment of inertia for a bar is 1/12 mb squared. So that's 1/12 the mass, which is 3 kilograms. I got that right here. And then b is the length. That's described on that table. And so the length is 4 meters squared. That's 1/12 of 48. That's 4 kilogram meters squared. So the first thing you do is find the moment of inertia. The next thing you do is find alpha. Because I know from Newton's second law that the net torque is equal to I alpha. That's the F equals ma, right, for a rotation. And so alpha is torque over I. That's 40 divided by 4, or 10 radians per second squared. Let me show you where I got those numbers. The 40 was that. That's my net torque. I left the negative off because I'm not really worried about the direction that it's rotating. It doesn't ask me anything about direction. And then the 4 is the moment of inertia, which I got right there. So that's my angular acceleration. That's my second step. 1, 2. And now the third step is I want to find the angular speed. And that's where you need to know the kinematics equations. Ooh, that was in chapter 7, wasn't it? Okay, I'll write them on the board next time. I didn't put it on your quiz, but I'll write them on the board. Can y'all remind me to write those equations on the board? Yeah, I'll remember. I'm sure one of the 110,000 people will tell me. All right, so no, there aren't that many people. There's just like 108 of you. So theta is omega naught t plus 1/2 alpha t squared. But I'm not looking for theta here. I'm looking for omega, and it's omega naught plus alpha t. So that's my third step, is to find omega. Omega naught is 0. I know that because it's initially at rest. It's usually 0 on these problems that you'll see. So it's just alpha times t. That's 10 radians per second squared. That's from part 2. Times 3 seconds. So it's 30 radians per second. 10 times 3 is 30. So you will see a question like that on the quiz. It'll be very, very similar to that. Like I said, if you look back at the old tests, you'll see similar 2-part questions basically on every exam. So make sure you practice those, and it'll probably be a free response question too on the next exam. Annie Jo?
So really you would just take what you got as n first and just multiply it by 7.
Yeah, because I'm just multiplying alpha, which is what I found here, times the time, which was given right here after 3 seconds. You can do that, right? Absolutely, all of you can do that. But it's going to be on the exam too. It'll be the free response, so it'll be a big deal on the exam. And on the quiz, that's a quarter of your quiz. 2 questions of the 8. Okay? I'm going to clear this. Another thing that you're going to see is an angular momentum problem. Let's see here. Is there a good one? Okay, this one is a good one. Number 13. This is, what was this, fall 18? Yeah, fall 18. Looking at number 13. I can tell the angular momentum problems because there's usually not a force involved at all. There are no forces or torques that come into play because angular momentum is not conserved if you have an external torque. That was true for linear momentum too, right? That linear momentum is not conserved if you have something pushing on the object, then your momentum changes. So I'm looking at this object, and I know that angular momentum, L, is conserved. That is Li equals Lf. And on this object, I just have one object here. I initial, omega initial will equal to I final, omega final. I can have more than one object, and we'll find a question where it shows you that. But you could have either of these. On this one, there's just one object, but it changes. That's like the figure skater, right? The figure skater is still a figure skater, but when she throws her arms out, her moment of inertia has changed. And then that changes the way that she rotates. So here, I need to identify what my quantities are. That's I initial. This is omega initial. And then this is I final. So notice that my moment of inertia has increased by a factor of 2. This is increased by a factor of 2. In order for my momentum to remain the same, this has to decrease by a factor of 1/2. So where omega I was 6, now it's going to be 3. Okay, so let me just work this out. So I have 10 times 6 equals 20 times omega final. So omega final is equal to 3. So if you don't see the ratio right away, if you don't just see it in the words, then you can, write down the equation and work it out. And that's okay too. No shame in that, right? All right. Can I clear this? This is easy for y'all? It looks easy now. Okay, but tomorrow when you sit down to the quiz and you don't have me there to say this is what you do, then it's not going to be easy. So make sure that you're practicing this on your own, because watching me do it is different from you doing it on your own. Y'all know that. Y'all are good students. Can I clear this? Okay. Let's see if we can find another problem. Well, no, let's do this one right now. Number 10. If you're not on the quiz, you'll have it on the exam. So let's go and take a look at it. I love ranking problems, especially for this topic. Ranking problems are just good problems. But here, I want to rank these from order of least to greatest moment of inertia. Remember, with moment of inertia, the moment of inertia is dependent upon the mass and the distribution of the mass. So how far away from the axis of rotation is the mass? And so with these, you want to look for the one that has the greatest moment of inertia. Let's see, this is actually least to greatest. So these are all the least moment of inertia, and these are all the greatest moments of inertia. I want to look for first which is the biggest and which is the smallest. Which of these do you think would be the biggest? A, because it has a lot of mass at a far distance from the axis of rotation. You got all this mass out here, and then you have this. So A is going to be the biggest. That gets rid of C and E. C goes away. E goes away. And then I want to look at the smallest. What do you think is the smallest? B or B? First. Well, look at B. B has a lot of mass, as much mass as you can get, in fact, at the smallest distance, which is 0. So this bar right here doesn't contribute anything to the moment of inertia because R is equal to 0 for this amount of mass. So this is going to be the smallest, B, but also recognize that B and C are identical. They're the same object. They're just sort of flipped on side. So B and C are the smallest, and they're also the same. So B would be the right answer. Why what now?
I don't understand why it's the smallest.
Okay, why it's the smallest. So here, the axis of rotation is right here, right? And I don't have any mass along the axis of rotation for this one. In fact, I have these two masses that are coming off. And given these masses don't go quite as far away as this mass does, but I still have twice the mass that's floating around. Whereas here, I have half the mass, which isn't contributing anything at all to the moment of inertia. Because for this little section, which is half the mass for all of this, R is equal to 0. And because R is equal to 0, it has no moment of inertia due to that. Now I have R due to this part, but that's only half the total mass. So whereas for A, all of the parts contributed to the moment of inertia, for B and C, only half of the thing contributes to the moment of inertia. We'll do another one, okay? Those are tricky sometimes. We'll do another one. With time, it'll sink in. So what did I say the answer was? B? Yeah, I can tell B too. You want to look for ones that are identical, and you can see that B and C are both the same, so I can get rid of this one too. So then really it becomes the question like you asked, which one's smaller, B and C or D? That's really the key question here that helps you find the right answer. But B and C are smaller. Okay, and I want to go to another test. That was fall 18. Let's go to fall 17. I'm looking for a particular kind of question to do with angular momentum. We can come back and do this one as well. Goodness, that's you. No, not that one. Let's go to fall 16. Oh, so number 5. So we did one of these in class. This is fall 16, number 5. We did one of these in class. This is a perfectly inelastic collision. Remember the perfectly inelastic collisions? That was where the two balls stuck together and they moved off at the same rate. Just like that. It worked out exactly the same as that. except now we're dealing with I and omega instead of m and v. So I have a bar, I have a flywheel like this. They're both spinning. The bar is spinning in this direction. The flywheel is spinning in this direction. And I want to know, after they come together, they spin at the same rate. And I want to know what is the total moment of inertia. So if you remember with the when the two balls were coming together like this, they both had a momentum, and then they stuck together and they moved off in some direction like that. It's exactly the same. I say L1 plus L2 is equal to L combined. I'm going to call that L12. All right, the first part is the initial momentum, and the last part's the final momentum. So I have I1 omega 1 plus I2 omega 2 is equal to I12 omega 12. Where 1, 2 is not 12, but it means like 1 and 2 combined. So I have these values. I1 is 8. Omega 1 is 2. I'm going to write a plus 2 because it's counterclockwise, just to remind me. And then the other is 16, and negative 4 is equal to the combined moment of inertia. What's I12? 24. It's going to be 8 plus 16, so that's 24. And then I'm looking for omega 12. So that's 16 minus 64 divided by 24 equals omega 12. 16 minus 64. 48. Is that 48? Divided by, so it's negative 2. Negative 2 revolutions per second. Notice I didn't have to convert it to radians here because the units all cancel out. When you're doing angular momentum, you don't have to convert to radians. It's really just when you're dealing with Newton's second law and rotational kinetic energy that you have to convert to radians. So that's A, 2 revolutions per second clockwise. Okay? I wanted to do another moment of inertia ranking. Can I clear this? Is it clear somewhat? Could y'all do this problem tomorrow? Or one like it? It's a lot like this problem. MV plus MV equals the combined masses times V. It's exactly like that problem, except now instead of using M's, we're using I's, and instead of using V's, we're using omegas. It's exactly like that problem. Be a perfectly inelastic collision. The initial, the first momentum plus the second momentum equals the final momentum. Okay, let's do another ranking. Then I'll open it up to questions. Okay, how about this one? Rank these, and it looks like we're going greatest to least. What's the greatest moment of inertia? Around which point? And this is a big, flat, square piece of metal, and the axis of rotation, like A, it would rotate like that. C, it would rotate like that. So what's the biggest moment of inertia, and what's the smallest moment of inertia? What's the biggest? A is the biggest, because at point A, look, I got all that mass that's at a far distance from A. That's as far as away I can get from having my mass from the axis of rotation. So A is the biggest. Which is the smallest? C, right? C is the smallest. So that gets rid of this one, and this one. So now really the defining factor is where do B and D lie? They're equal because notice B and D are the same. I just flipped, they're symmetrical. So the answer would be E is the right answer for that one. Okay? Looking at how far your mass is from the axis of rotation. And that'll tell you what your moment of inertia is relative to other points. All right, let's look at An energy problem. Let's look at number 1 here. So on these energy problems, of which you will have one, I mean, I picked ones from all the different topics in this chapter. You need to be careful about, is it asking for the total kinetic energy, the translational kinetic energy, or the rotational kinetic energy? Look for those words. Really just looking for total or rotational. Every word's important in these problems, so make sure you're reading them carefully. Here I want to know the total kinetic energy. And the total kinetic energy is going to consist of translational, 1/2 mv squared, plus rotational, 1/2 I omega squared. And usually in these, you're going to have to convert either your linear velocity to an angular velocity, or vice versa. So don't forget that v is equal to omega times r. Okay, so I don't know if I gave you that equation either, because I think that was chapter 7. What a jerk. I'll give it to you tomorrow, okay? I'll write it up on the board. So in this one, I know the mass, there's m. I know the speed, v. And then I also, let's see, I know omega is 4 radians per second. And then I also know r. I was kind of nice in this problem because I gave you both v and omega. But look, I don't need to give you that because if I give you v, 2 meters per second, and I give you r, 0.5 meters, then you can figure out what omega is. Omega is 2 divided by 0.5, or 4 radians per second. And if you look at other problems, you'll see that sometimes I don't always do that. But in this case, I did. The one thing I didn't give you is I. And so you need to find out what I is. I is on that table with all the shapes. And I for, let's see, this is a disk. So what shape am I going to be looking for? A cylinder. I'm going to be looking for a cylinder. And I for a cylinder is 1/2 mr squared. That's 1/2 of the mass, which is 8, times r, which is 0.5 squared. That's 4 times 1/4, so that's 1. So now I'm ready. I have 1/2 of the mass, which is 8, times the speed, which is 2 squared, plus 1/2 of 1 times omega, which is 4 squared. 4 times 4, that's 16, plus 8 is 24 joules. Sometimes in problems, I don't ask for total kinetic energy, I ask for the rotational kinetic energy, where you're just doing this part, where you're just finding 1/2 I omega squared. Just be on the lookout. I'm not sure which I gave you. I don't even remember what question it was. Okay? I could do that, right? 100%. Especially you people. I call it you people especially, because you're here. I'm giving you all the answers right here. Right? Okay, what do you want to look at? Those are the big classes of problems, but what else do you want to look at?
I just have a question. How do we know when it's going like counterclockwise versus clockwise on like the network?
Okay, so let's look at that. Students have issue with that. Even the best students, right? Right? All right. So here, like number 7, on this one, first of all, you identify the forces that don't cause a torque. That one doesn't cause a torque. And this one also doesn't cause a torque, right? Because it's like, it's not making it rotate in any direction. And then I like to put a pencil on my paper. I put a pencil right here and I pull on it. Then if I pull up in this direction, then I see that it makes it go clockwise.
Okay.
But you can sort of see that if you just draw it on your paper too. Because this force, which is acting here, is going to pull up, and then it's going to rotate around. And so that is clockwise motion. And then if I have a force here, that's going to cause it to go like this, and that is counterclockwise motion. And even if the forces are at an angle, they're still going to cause motion in the same direction. It's just only a component of that force is going to cause it. The other component of that force doesn't cause any torque at all because it's a theta of 180, and the sine of 180 is 0, or 0. Does that answer your question? But use your pencil if you want on your paper, or just sort of draw in the direction of the force, but draw it in a circle. And then think, oh, is that clockwise or counterclockwise? You can always look at your watch and see, oh, it's going in this direction, so that's clockwise. Oh, loser. What is it, Annie Jo?
Alright, I remember doing a question like number 5.
Yeah.
Class. Are we gonna have to going down?
Good, yeah. So you certainly have moments of inertia problems where I just ask you the moments of inertia. Remember with moments of inertia, there are two different types of problems. There's the ones that like this where the discrete particles, individual particles, and then there's the kinds with the shapes. And I actually think that you see both of those. I don't remember exactly, but certainly on the test you'll see both of them. This is a discrete particle. And the way that I can tell is because all those shapes are rotating about an axis that's internal to themselves. Right, like the cylinder rotates about this axis, or it rotates about an axis through here. Same for the bar, like it rotates about an axis through the center of the bar. So these objects are rotating about an external axis of rotation, external to the body. So even though they look like spheres, I don't give you any kind of information about the spheres. Like I don't tell you the radius of the spheres because it's not important. We treat these as discrete particles. And so you need to identify first, am I dealing with discrete particles or am I dealing with a shape? And you can tell by the axis of rotation. Is the axis of rotation internal to the object? That would be a shape, a sphere, a disk, a cylinder. Or is it external? In this case, it's external. And you would say I is the sum of mr squared. And so it would be 1 times 1 squared. That's 1 kilogram times 1 meter squared. Plus 1 times 1 squared plus 4 times 2 squared. 1 plus 1 plus 16 is 18. Cool? Yeah. Sometimes, oh, where is it? There was a problem. Oh, like this one. This one is actually a combination of the two. Because here I have a shape, which is a disk. And I know for a disk, I is 1/2 mr squared. But then I also have an object, a discrete particle. And I know for that particle that I is equal to mr squared. So in this case, I have a combination. And to find the total moment of inertia, I would add them up. 1/2 mr squared plus mr squared. Different masses and radii, of course. So it's 1/2 times 3 kilograms times 2 meters squared plus 4 kilograms. Oh shoot, I don't give you the radius. What's the radius? 80? What's r squared? Why? Why is it 2? Oh, come on.
Just went along with Would it be 2 if it be the same axis?
It's 2 meters away from the center still.
Right. It's the radius of the circle. So the reason we use 2 is because it's this distance, 2 meters. And I know that that's 2 meters. It's the same. Okay? So that's equal to 6 plus 16 or 22. Okay? Be prepared for any of those or all of them. Let's look at these, number 2, because I have some variant of this problem on all tests where I say something about the angular momentum, and then I say something about the energy, and sort of how is the angular momentum and the energy different, right? Because remember, we saw this in class one time where I said one object has, what did I say? Well, let's just look at this problem. So 2 objects have the same angular momentum. object 1 is spinning twice as fast as object 2. So I'm going to write the equation for angular momentum. Object 1 is spinning twice as fast as object 2. So it has twice the angular speed, but it has the same angular momentum. So that means it's going to have half of the moment of inertia. Y'all follow what I just did there? But the first object has twice the angular speed, but because it has the same angular momentum, it has to have half the moment of inertia. And now I want to know, how does that impact the energy of object 2 is 10 joules. So what then, this is my object 1, what's going to be the energy of object 1 compared to object 2? So, what? No, because watch. Because energy is 1/2 I omega squared, and I have twice the speed, but 1/2 the moment of inertia. So it's twice the energy. This object that's spinning twice as fast with half the moment of inertia will have twice the energy, or 20 joules. There's a problem like that on every test. That's something similar, some variant of that, where it's looking at the relationship between momentum and energy. And I like to give those, and you'll see it tomorrow, of course, that because it just helps you to think about the relationship between the variables. It just helps you to think mathematically, and that's why I like it. It's not so much momentum or energy that I'm really concerned about, but just that you're able to think mathematically. What?
I've got it until you wrote all the numbers and letters.
And you didn't really get it
Well,
before.
because like if it's going twice as fast, then it's gonna have twice as much energy because it's going twice as fast.
No, because if it's just going twice as fast, it'll have 4 times the amount of energy, right? Because it's 1/2 I omega squared. So if it's going just twice as fast, it's going to have 4 times the energy because there's a quadratic relationship between kinetic energy and speed. We saw that before with Ke and V, right? Kinetic energy and V. And it's true here too. But so I would say it would be 4 times energy, it would be 40. But I also have this 1/2 factor that I have to consider. That if omega is twice what it was, then moment of inertia is half what it was. This was a particularly tricky one because the numbers sort of cloud people's vision. Or maybe the numbers make it easier. Like for me, the numbers make it harder. But when it's just variables, it seems a little easier. Okay? Yes, you have to get a question like that correct. All right. Let's see what else we got. Any other things you want to look at in particular? No? You want to stop? I'm okay staying for another 15 or 20 minutes, but if it's up to you. You good? You good? You sure? Okay, let me stop.